Okay, so let's talk a little bit more about angular momentum. So what I mentioned at the end of the last video is that just like linear momentum, angular momentum is conserved, and then the criteria for that is if the net external torque on a system is zero. Okay, and this is a very powerful concept because here's what it means. So L is equal to, for a rigid object that's spinning, I omega, okay? And if this object experiences no net torque, then its angular momentum must be conserved. Or if you have a system of objects, their combined angular momentum would have to be conserved. Okay, well, let's think about an object, okay? Let's say that we have a way of causing the moment of inertia of an object to decrease, okay, or to change. If you're able to make I decrease without causing any external torque, which means that this angular momentum would have to stay constant, then what has to happen because of that is that the angular velocity would increase. Okay, so anytime something is spinning and it's able to decrease its moment of inertia, in response to that, the angular velocity increases. It spins faster. Okay, so there's some really good examples of this and how this places where you would see this in nature or in the world on page 290 to 291. I encourage you to take special time to read through those and understand those examples because they're just, I personally think this is just really fascinating. Okay, and this is why when you think about our solar system and the galaxies, this is why everything is moving in circles around each other instead of crashing into each other. Okay, so let's think about this. Let's say you have two objects in space flying towards each other. Okay, and if these are just two objects flying towards each other, then let's say this is our system, there would be no external torque on this because there's no friction, nothing from the rub against, anything like that. Okay, well, this system has a certain amount of angular momentum. Okay, well, as these objects fly, considering how big space is and potentially how fast they're moving, the chances of them colliding is extremely small. Okay, but based on their speed and based on the distance they're going to pass by each other, they have a combined amount of angular momentum. And let's say that as they pass by each other, their gravitational forces cause them to pull together, okay, then these objects might start spinning, okay, at least they'll cause each other to kind of spin off. If they pull hard enough, then they'll cause each other to spin around in a circle, okay. So that's kind of like an explanation of why, like, as planets were formed or stars were formed, they're pulling particles together. As those particles pull in, there's going to be some net angular momentum to one direction or other, causing it to spin. Okay, so like in this case here, not only do those things spin, but as they get spin closer and closer together, the closer their spin is, then the faster they're going to spin, because if that moment of inertia gets smaller, that angular velocity increases. Okay, and there's a really cool example in your book on that page 291 of a neutron star. Okay, if a star has angular momentum, I omega, and it collapses in on itself, well then I is going to get much smaller. It's going to decrease a lot. And in return, that omega has to get much bigger. Okay? And so what you get is these really small stars, okay, that have a very fast angular velocity. And on the book it says up to 800 revolutions per second. Okay? a giant, well, I mean, it's small for on the scale of stars, but much bigger than our planet. So you have this giant object that's rotating 800 times every second because of it collapsing in on itself. Okay, apparently, according to the book, the sun just completes one revolution every month. Okay, so you can see how that change in size causes that increase in angular velocity, and it's just, I mean, it's just crazy. Okay, so another really cool example is like if you were standing on a boat, okay, in the middle of the ocean or somewhere. Okay, so here's a person standing on the boat, and let's say they decide to spin in circles. Okay, well, as they're spinning in circles, they're exerting a torque on the boat, causing the boat to spin this way. Okay, and again, in this case, that angular momentum would have to be conserved. So let's say that you and the boat have, as a system, have zero angular momentum. In the process of you spinning, you're creating a net angular momentum to one way, and so the boat will spin the other way to compensate. Okay, and then another example on that page is kind of showing how that's actually, if you were in space and you wanted to steer like a spaceship, since there's nothing for it to push off on, one of the ways that you could control it is if you had some disk that you could rotate, and by causing that disk to rotate, you'd force the boat to rotate, or the spaceship to rotate a different way. Okay, and then the kind of crazy example they had here is that when they sent a spacecraft to photograph planets, and as it was flying by some planets, it was recording video, and just the rotational motion of the film spinning in that camera caused the entire spaceship to start to rotate. And so in order to prevent the rotation from happening, they had to actually fire off the engines to compensate, okay, to keep that spacecraft on its orientation. All right, so angular momentum, as I was saying, just a really, really powerful concept, okay, and so we'll get into some examples of it now. Okay, so here we have an example where there is a beetle on a disc, okay, and it's spinning around, okay, and what's going to happen is the beetle is going to crawl towards the center of the disc, okay, and it's going to ask us how these factors change for this system, okay, and we're actually going to track it with a graph. So let's say that we have a graph showing moment of inertia on one axis and angular velocity on the other axis. And so we'll say this is before, and then we'll do one for after. Okay? And so what's going to happen is this. The disk has some moment of inertia, okay, and the beetle has some really small moment of inertia. Okay? Now, as the beetle crawls to the center, this one won't change. Maybe this one was like kind of big before them. Okay? So the moment of inertia of the disk here won't change, but the moment of inertia for the beetle is going to get smaller, okay, as it crawls to the center. Now let's say that they're rotating at some speed here before, and we have angular momentum, I omega plus I omega. Okay, well, as the beetle crawls to the center, this moment of inertia decreases, okay, it gets smaller, and so there has to be a compensation, right? And we'll just say I plus I omega, since they're traveling at the same speed. Okay, and so then on this side we have I plus I times omega as well. This is omega final though, and this is omega initial. And so this value here for the beetle got smaller, which means that if this is smaller than that, but the total angular momentum of this system has to be conserved, then we're going to compensate by increasing the angular velocity. Okay, so as we look at this, the rotational inertia of the system would have decreased because the beetle got closer to the center. okay, the angular momentum of the system would have stayed the same, okay, but the angular speed of the system would have increased, okay? And I'm going to make a little chart here. Okay, so for the beetle, or for the disk, and for the beetle, I want to show how rotational inertia changed, angular momentum changed, and angular speed changed. Okay, let's say the beetle for the disk and the system that combines both of them. Okay, and so this is kind of important to think about. So for the disk had a change in I, or it didn't change, so that stayed the same. For the beetle, it didn't increase, it decreased. Okay, now for the system, the I also decreased. Now the rule is that for the system, angular momentum must remain constant. Okay, but for both the beetle and the disk, individually their angular momentums changed because both I and omega changed. Okay, and so for the beetle, because the I decreased, it actually caused the angular velocity of the beetle to angular momentum of the beetle to decrease as well. Okay, because even though it rotated faster, it wasn't enough to compensate for just the decrease. All right, the disk had an increase in angular momentum because while this stayed the same, it started rotating faster. And the amount of increase it had was equal to the amount of decrease from the beetle, so that we could have a net change in momentum of 0 for the system. Okay, and then also angular velocity increase for all three of them. So here's something really important to think about though. The disk had an increase in angular momentum from the beetle. The beetle had a decrease in angular momentum from the disk. Okay, they exerted equal and opposite torques on each other in order to change their angular momentums. Okay, the reason we track it as a system is so that we can say that the momentum was conserved, but when you look at them equally, there's external torques acting on them from the other object, okay, causing their angular momentums to change. Okay, so if you think about when we talk about the torque here, that torque would have come from the friction between the disk and the beetle as the beetle was walking towards the center. And that's what caused the angular momentum of the beetle to decrease and the angular momentum of the disk to increase. Okay, but at the end of the day, it's the same for the system.